So we're using some of the concepts of ratios and proportions in section 7.2 when we're talking about similar polygons. And when we say any sort of similar figure, that just means that they have the same shape but not necessarily the same size. You might want to think back to dilations for an example. We can abbreviate the phrase is similar to with this symbol. So it looks kind of like the approximate sign just with one of those. And again, we read that as is similar to. We can use ratios and proportions to decide whether two polygons are similar and find the side lengths of those similar figures. So for our rules down here, we know that two polygons are similar if their corresponding angles are congruent and if the length of corresponding sides are proportional. So for congruent figures, we need them lengths to be the same. For similar figures, we just need them all to be in the same proportion. But for both congruent and similar figures, we need them to have the same shape. So that means all the angles should be the same as their corresponding. So A and G, those corresponding angles will be the same. They're both right angles. B and H, same thing, both right angles. We need C and I, those corresponding angles should be congruent. And D and J should also be congruent since those angles are corresponding. And when we say the lengths of corresponding sides are proportional, you want to think that they should have some sort of scale factor that are all the same. So the length of AB over GH, if I use that ratio, should be the same as if I compare BC to HI, those two corresponding sides. CD to IJ should be the same ratio, and same thing DA over JG. So if I look at all of those four sides, they should all be in the same ratio, so the same scale factor from one figure to the other. Scale factor is the ratio of the corresponding linear measurements of two similar figures. So linear measurements, you just want to think lengths of the sides. The ratio of the lengths of the corresponding sides in this figure that we have down here, triangle ABC and triangle XYZ, we can just use one pair of corresponding sides to find that scale factor. So if I look at BC over YZ, that's a length of 20 over a length of 8. So that ratio, if I reduce that, 20 over 8, would be 5 to 2 for the ratio. So the scale factor of triangle ABC to triangle XYZ is 5 to 2, or again we can write that with a colon, 5 to 2. So it is also important which direction we're going. ABC to XYZ has ABC first and XYZ second, so we don't want to write 2 to 5. That does have to be 5 to 2 because we kept it in that order. So we can also see, if you want to test that rule from up above, it does work the same for all of your other sides. So we found BC to YZ, but it could work for the other sides as well. So AB to XY, that's a length of 15 to 6. We already found BC to YZ, but if I also look at AC to XZ, those should all reduce to the same ratio, so they should all have the same scale factor. If they do not have the same scale factor, so if one of those is wrong, those figures would not be similar. They would not be in the right proportion. So now we're trying this with triangle MNP and triangle SRT. And first we're told that they're similar to each other, so not that they're congruent, but remember just that symbol is going to read as is similar to. So first, if we're asked for the pairs of corresponding angles, congruent angles, we can go back just like what we did with congruent triangles. It should match just based on the name. So angle M and angle S should be congruent, angle N and angle R are congruent, angle P and angle T are also congruent. We should be able to see that from the figure too. M and S, N and R, P and T, those are your three congruent corresponding angle pairs. And now if we want to make that extended proportion for the ratios of the corresponding sides, same as with your last figure, you just got to make sure we're matching corresponding pieces. So MN over SR, so that ratio of MN to SR would be the same as the ratio from NP to RT, and that should also be the same as the ratio from PM to TS. Again, if they're similar, that ratio should all be equal. And we're going to use that in problem 2 to test if they are similar. So if so, we're going to write a similarity statement and give the scale factor. So in our first example, we can just look in terms of smallest to largest sides. So it looks like all of the angles are congruent as long as they're corresponding. So it looks like, yeah, we have matching angles that are corresponding and congruent. But when I look for the sides, the shortest side here is JM, so that's a side length of 6. Shortest side of this figure, I guess it's a tie, but we have a side length of 6 as well. So that kind of implies that our scale factor should be 6 to 6 or just 1. But if I look to the next smallest side in my first polygon, that JK has a side length of 12. When I compare that to the corresponding side here, side length TU, 12 is not the same ratio as our previous answer. So our previous ratio was 6 to 6. So I can see that if my next side is not in that same scale factor, those figures are not congruent, or sorry, not similar. So next problem, same thing. We just want to see, first of all, are there corresponding angles that are congruent? So yep, A would be congruent with D, B would be congruent with E, and C would be congruent with F. So I have 3 corresponding angles that are all congruent. And now if I'm comparing the ratios of their sides, if I'm testing that proportion, again, if I start from smallest to largest, 8 from one triangle should match the side that's shortest in the next. So 8 to 10 I compare as a ratio. And that should apply for 12 to 15 as well, my next smallest side. And the largest side should also be in that same ratio, 16 to 20. If I reduce all of those ratios, we see that they're all in the same scale factor, they're all in the same ratio, and that ratio is 4 to 5. So yes, those figures are similar, and what I left out here was our similarity statement. So you'd want to add in that triangle ABC, so that first triangle is similar to the second triangle. So remember, is similar to is going to be, whoops, didn't really make it there, but that little squiggly, so is similar to triangle, we want to keep that in the same order, so if it was ABC, your next triangle is going to be D, E, and then F. So if a similarity statement similar to a congruence statement just uses similarity instead of congruence. And also if you want to match which part comes first in that statement, you can look back to the angles. So A matched with D, B matched with E, and C matched with F. So I have it in that order. So next question, if we're asked to find individual values, so we're not asked if they're similar, we're just told that they're similar and want to find the actual missing side lengths. If we want to find X, for example, X is the side FG, so that length, and the corresponding side would be BC, but I can't just use that as a ratio, X over 7.5, because I don't know what the scale factor is. So in order to find that scale factor, we're going to look for a completed set of lengths that we can compare. So DE has a length of 6, AD has a length of 9, and those two should be corresponding. So if I use the ratio 6 to 9, that should tell me the scale factor that I'm using to go from the smaller trapezoid to the larger trapezoid. So if I use that scale factor, 6 to 9, that should be the same as my smaller side X to the larger side 7.5. And now that I have that proportion set up, I should just be able to cross multiply. So 6 times 7.5, I get 45. 9 times X would be 9X. Just got to finish by dividing by 9, and we get that X should be 5. So that missing length was 5. Same idea if we're looking for Y. This time it looks like the side that's corresponding with Y is AB, so that length of 5. If I use that same scale factor, so 6 to 9, could have also used 2 to 3, so we could also reduce those scale factors, although we can see that we could solve it without reducing. I would just be looking to cross multiply. So if I'm using the scale factor 6 to 9, again that was small side to bigger side, that should match up with the ratio Y to 5, because that's smaller side to bigger side again. If I cross multiply, I get 9 times Y equals 6 times 5, which is 30. Divide by 9, and we can leave that as a simplified fraction. That would be 10/3. So as long as I'm using that correct ratio, as long as I find a completed pair, so 6 and 9 to determine my scale factor, I use that same scale factor to find both X and Y, because those should also use the same scale factor. Next question is a little bit different, asking us that our class is making a rectangular poster for a rally. Our poster's design is 6 inches high by 10 inches wide, which I've kind of drawn in this diagram. The space allowed for the poster is 4 feet high by 8 feet wide. So the first thing you want to do on this type of question is make sure that you're using the same units. Instead of feet and inches, I converted those both to inches. So that second pair of measurements, 4 feet would be 48 inches high, and 8 feet would be 96 inches wide if I multiply both of those by 12. So if we want to find the dimensions of the largest poster that will fit in that space, the first thing we have to do is figure out which dimension we're going to fill up first, either the height or fill up the width faster. And in order to do that, I can take that those measurements and divide to find the scale factors. So if I was filling up all of the height, I take 48 divided by 6, and that multiplier was 8, so it basically means it's 8 times as large if I'm making it fill up all the height. And if I take that other scale factor, so 96 divided by 10, that would be saying I would be magnifying it by 9.6 if I wanted to use up all the width. But if I did use a scale factor of 9.6, I wouldn't have enough room to fit all the height, because again 9.6 times 6 would be bigger than 48. So since I couldn't use that second scale factor, it's too big, I have to use the smaller of the two measurements to multiply my largest dimensions. So if I use that multiplier of 8, I just go back and use those dimensions again. So 8 times 10 gave me 80 inches for the width, and 8 times 6 gives me 48 inches for the height. So the largest poster that will fit is 48 inches by 80 inches. Next question, same idea. If we're given different dimensions this time for the space that we have, now we have 3 feet of height and 4 feet of width. Again, first thing you want to do is convert. So 3 feet is 36 inches, 4 feet is 48 inches, and same idea, we want to think what's the biggest multiplier we could use for both. So if I take the height, 36 divided by 6 would be an increase of 6 times, and if I take the width, 48 divided by 10 would be an increase of 4.8 times. But again, we can't use the bigger one because if I tried to take that bigger measurement and use the width, I would need 60 inches, and I only have 48 inches to use. So we're going to take the smaller of those two numbers, multiply both of your original dimensions. 4.8 times 10 gives us 48. 4.8 times 6 gives us 28.8. So I know my new dimensions are 28.8 inches and 48 inches. Again, those questions you want to think the smaller of the two numbers is the one that's going to give you enough room. In a scale drawing also, the lengths are proportional to their corresponding actual lengths, so we're going to be using similar figures. The scale is the ratio that compares each length in the scale drawing to the actual length. Then lengths used in a scale drawing can be in different units. So for example, scale might be written in a lot of different ways. We could spell it out using the word 2. We could write the word, not the word, but we can have an equal sign comparing the two. Or we could also use that colon to demonstrate a ratio. So in this problem, we have a scale drawing of the Golden Gate Bridge. The distance between the two towers is the main span length. So on the drawing, the main span is 6.4 centimeters if I was to measure from one to the other. And we want to use the actual length, we want to find the actual length by using that scale given in the corner. So I can set this up using a proportion. And there's different sorts of proportions you can use. The one that I used was the length of the main span in the drawing was 6.4 centimeters. And in our scale, that was 1 centimeter. And if we want to find the actual length, that's the part that's missing. And in our scale, that was 200 meters. So if I set up my proportion, I can cross multiply. 6.4 times 200 should be equal to x times 1. And that eventually gets us that x is 1,280 meters. So 7.3 will be leaving for class, but also come in prepared to answer questions on 7.2.